Hey all. So my wife and I, actually my wife just bought me a Galileo thermometer, and so she was asking me some questions about how it works, and it's actually all based on density and buoyancy force, which is what we were just talking about in class. And so I thought, in explaining it to her, I would record my explanation so that you all can have a better understanding of buoyancy force. So I want to start by talking about a hot air balloon. Hot air balloons are able to float off the ground because of buoyancy force. So if we think about the hot air balloon that we have here, all right, if we were to draw a free body diagram for it, it has an upward buoyancy force pushing up on it, and it has a downward force due to gravity, its weight, okay? And so if the hot air balloon moves up at all, what that means is that its weight is less than its buoyancy force, right? Net force is up means it's going to move up. Okay, that sounds good. It's got some force going up. That's cool. But normally, the kind of things that give forces up are things like propellers and engines and jets and stuff like that. But here, the buoyancy force is a direct result of pressure difference in the air, the pressure gradient that we talked about in class. And so the way that we quantify buoyancy force, what it's equal to is buoyancy force is really just equal to the weight of the fluid displaced. So weight is mass times gravity. And since it's the fluid displaced, this is the mass of the air that it's pushing out of the way. So what this means, this equation right here, this inequality, I should say, what this means is that the weight of the balloon, so if I were to write it as mass of the balloon times gravity, and that's the balloon, the basket, the people in there going for their picnic, everything, that all weighs less than the air that it's displacing, the mass of the air times gravity.
Can I ask a question?
Yeah.
How can something have an upward force?
How can just something in general or the
Yeah.
balloon in particular?
Like you said, it doesn't have a thrust. How can it have an upward force?
Right, so the reason it has an upward force is just crazy and why I love buoyancy force in general so much. Let's say, like a helium balloon or something. It's your birthday and you get a balloon from Chan's Chinese restaurant, as you guys are going to see in my video that I show in class. Anyway, so you have this balloon, right? What happens is the air around
It's
it...
Quan's.
Oh yeah, Quan's. What did I call it?
Chan's.
Oh, whoops. Quan's was the name of the place. Sorry. Anyway, so what happens is air has pressure. And so there's pressure pushing on this from all sides. The air is physically pushing on it. All right? So there's air pressure on all sides. But what happens is, because of the pressure gradient, because pressure is higher down lower, what you have is you have a situation where the bottom of your balloon, this side of the balloon, has a pressure on it, let's call it P1, and the top also has a pressure on it, which we can call it P2, and because of pressure gradient, what we learned about in class, P1 is actually larger than P2. And so if there's a difference in pressure, there's a difference in force. And so what's actually pushing up on the balloon, whether it's Quan's balloon here or the hot air balloon here, what's actually pushing it up is the air. The air pressure is pushing it up.
It seems like it shouldn't be able to push it up because the pressure gradient isn't that big, right?
I know, that's what it seems like. And we're talking about, like, for a balloon, right? What is this distance? We're talking about a difference in distance here of, half a meter or less, just the size of a balloon. And the difference in pressure over just that small amount is enough to generate an upward push, an upward force.
It seems really nutty.
It is really nutty, and that's why buoyancy force is so awesome. I'm glad you appreciate its nuttiness. So, yeah, that's why there's that upward force. Again, it's the pressure difference. And so what happens is the hot air balloon is pushed up because of that pressure difference. And the way we quantify what is that amount of pressure difference is by saying buoyancy force equals just the weight of the fluid displaced, which is a whole nother cool conversation of how to prove that the pressure difference is equal to just the weight of the fluid in that area. But for that, you'd have to take like a calc-based physics class. So that's beyond the scope of our course. But cool, fun fact. So let's look at this equation again. So here we see that the weight of the balloon must be less than the weight of the air, okay? Well, a lot of times with fluids, we don't deal with mass. Like, what is the mass of a ball of air? Well, you can't really just put a ball of air on a scale, and you're not going to be able to weigh it very properly. So what a lot of times we deal with is density and volume instead. So if you remember from class, density is equal to mass divided by volume. And so you can rewrite mass is equal to density multiplied by volume. Okay? So what we can say is we can substitute mass equals density times volume. All right? So if we go back up to our equation up here, where we're talking about the weight of the balloon versus the weight of the air, what we can say is that mass of the balloon, which is really just the density, average density of the balloon, times the volume of the balloon, times gravity, must be less than the density of the air times the volume of the air times gravity. So, if we think about it, the density of the balloon and the density of the air, those are properties of the balloon and the air. But the volume of the balloon and the volume of the air displaced, how are those two going to compare to one another? Well, they should be the exact same, right? The volume of the balloon is the amount of air it's displacing, right? Because it's what's pushing the air out of the way. So those two are the same. And gravity, G is G. So what we can do is we can actually cancel these out. And what we see is that in order for a balloon or any object in a fluid to float, the density of that object must be less than the density of the air. And if you want it to stay exactly in place, then their densities must be equal to one another. So another way to think about buoyancy force, which is a lot of times what you hear people talk about, is in terms of density. Density of the balloon must be less than the density of the air in order to float.
So were you just deriving that equation? Is that what you were doing?
Yeah, I was just
that mumbo jumbo?
showing this relationship in terms of how it relates to the weight and what we've talked about in class.
Got it.
So I was doing all of that so that we can talk about
A rocket ship.
Galileo Thermometer. So I'll probably bring this into class, but what this is it's basically a cylinder of water. So this blue, this is all just water, okay? And then suspended in this water are these little glass globes that have different color water in them that are fixed sizes, and they each have different densities. So number 4 is the largest density, then 3, then 2, and 1 has the lowest density. All right, so just in case you're wondering what this is, you got density 1 is the smallest, then density 2, then density 3, then density 4. The cool thing is that each of these numbers...
Are those supposed to be P's?
No, it's the Greek letter rho.
Oh. But some of them look like P's and some of them look like E's.
Okay, well...
Sorry.
That's all right. They know that this is a problem for me as well. But I actually have these typed out on my PowerPoint slides, and they do look a lot like P's. But it's the Greek letter rho. So it's a P that's just a little bit curvy on the tail. So what happens is this thing can actually be used to determine temperature. It's really cool. I have one in my living room right now, and I put it in front of the fire to watch each of these move down. As the water is heated up, these different globes have moved downward. So first the 4 moved down, then as it got warmer the 3 did, then the 2, then the 1. So the question is, why is that? Why, as the water warms up, do different globes begin to sink? Okay, good question. Well, for number 4 to sink, what that means is that the density of the water, so I'll use rho still for density of the water, in order for 4 to sink, the density of the water must be less than the density of number 4, right? Because again, things float if their density is less than their fluid, and they sink if their density is more than the fluid. Okay, so since the density of the water is less than the density of object number 4,
Turns into
object
a
number
rock.
4 sinks like a rock, because rock's density is more than water, and so therefore they sink. A piece of wood, its density is less than water, and therefore it floats. But these things are so close, all of them are so close to the density of water, what happens is, as water heats up, so as the temperature of the water increases, what happens to the density? As the temperature of the water increases, the density of the water decreases. All right? So what we see is as the water gets warmer, its density goes down. So what you can think of is, let's say the water is cold, the density of the, let's rewrite that. If the water is cold, the density of the water would be up here. It would be greater than even number 4, and that would float. Then as the water gets warmer, the density moves this way. Once it gets to this temperature, maybe this might be, I think on our thing it's something like 68 degrees. At 68 degrees, the density of the water is at this location, in between 3 and 4. 4 sinks, 3, 2, and 1 all float. Then, as the temperature increases some more, once it gets to 72 degrees, that's a 2. Once it gets to 72 degrees, its density is now at this location. And so now 3 and 4 sink, 2 and 1 still float. As it heats up some more, its density continues to drop. And so at 76 degrees, its density is here. 2, 3, and 1 will all sink. 2, 3, and 4 will all sink, and 1 still floats. And then finally, once it reaches about 80 degrees, they will all be sinking. So based on which ones are floating and which ones are sinking, you know the approximate temperature range. Galileo developed this tool a very long time ago and used it to give you a coarse measurement of temperature. So does that help clarify things at all? It's all about the density of water decreasing as temperature increases. So where its density is at changes with temperature, and as a result, different objects will float and sink in it because of buoyancy.
So does that mean the water gets lighter?
Good question. Density equals mass over volume. The total amount, the quantity of water doesn't change. So the mass, this value here, is constant. So what happens is the water, this is what changes.
I can't see because you're left-handed.
Sorry. The volume is what actually changes. As it heats up, it expands in size, and so it actually takes up more space. So as it gets hotter, what would happen is the water expands up just a tiny bit up into here, a little bit larger. And so as the volume increases,
so the amount of water
density
in the
decreases.
space is lighter.
Say again?
So like the amount of water taking up the space of one of those globes is lighter.
Exactly. Exactly. The water displaced by a given globe becomes lighter, less massive, as the temperature increases,
Okay.
because the water expands. So hopefully that made some sense. We at least had a good time making the video. So anyway, hopefully that helps you guys think about density. If you have any questions, as always, let me know.